our methods of testing these hypotheses rely heavily upon the concept of sampling. And as we've seen, sampling really draws upon the central limit theorem in that we know when we take a sample that it is not likely to be exactly the population mean, but it will be oftentimes quite close, and sometimes it'll be further away. And in fact, we can build these normal distributions because of the central limit theorem, and we can calculate exactly how likely it is to be a certain distance from the population mean. So because we know that these sample means are going to bounce around, that's going to produce some type of it's going to lead to potential error. Now, what we're doing here in chapter 10 is we are assuming that the mean is what we've laid out in the null hypothesis, and really we're relying upon the likelihood of the distribution here to say that when we get a sample mean relatively close to the hypothesized mean, we won't reject the null hypothesis. But if we find some value, a sample mean quite far away, beyond some level in the rejection region, as we've been calling it, if we find enough evidence, if it's far enough away, we'll reject the null. But of course, that can happen by chance, and it does happen by chance a certain amount of time, right? And this is dependent upon our alpha, but for instance, in the case that we're looking at here, an alpha of 5%, we know that we're going to, if in fact the null hypothesis is true and the mean is 10 centimeters, 5% of the time we're going to find a sample mean. Even when the population mean is 10, we would find a sample mean beyond our critical value in our rejection region. When we do that, we find a sample mean that is far enough away that we go ahead and reject the null, when in fact the null is true. So again, assuming that this null is true, we would find something far enough away to reject it, even though the null is in fact true. And that's what we refer to as a type 1 error. Okay, so we rejected the null, okay, but in reality the null is true. Okay, and that's an error that we have to contend with, and in fact we know the likelihood of that occurring, and that's really what we're deciding upon when we choose alpha. So if we chose an alpha of 10%, we'd have a 10% error, type 1 error, I should say. So that's one of the two types of errors we need to contend with, and we know the likelihood of that occurring. The other type is the flip side of this. So it's cases where we do not reject the null when in fact the null is false. So this is a little tougher to wrap our heads around because we're building these normal distributions in terms of, or the one, say for instance the one we have drawn here is assuming the null is true. But really in this case, so type 2 error, a type 2 error is the null is not true, but we happen to find a sample mean from this other population that falls within the range that we do not reject the null. So let me try to draw this. Might be easier to just start fresh there. So really when we think about this, let's imagine this is the 10 that we've been talking about. Okay, and for instance in the past example, we found a value that was, let me refresh my mind, it was negative 1.5. Kind of mixing, so 9.985. We found a value of 9.985. Okay, and that was not in the rejection region. And so we had a cutoff somewhere down here, Okay, we haven't figured out that exact value, but we know that we turn this into a z-score. This was a z-score of negative 1.5, and it was not extreme enough to reject. But a type 2 error, thought I was in the right spot. A type 2 error results when, let's say for instance, the mean was not 10. Okay, so let's say the mean was something down here. I don't. Let's say the mean was, or is, 8.5. That's going to be way too extreme. So let's say it's 9.7. Okay, that could be the case. Maybe we have some major issues with our chopstick production line, and but we happen to get a sample out of this population that is really a mean of 9.7. We happen to get a value that is high enough that it still falls in the acceptable range for our original null hypothesis. So that is going to occur as well from time to time, and that's what we refer to as a type 2 error. Now, we don't have a defined percentage time that happens going into it. We can calculate, and we'll do this in a future video, but we can calculate the chance that, for instance, when we take our sample of 9.985, we can calculate the chance that itself is a type 2 error. But going up, when we set up our initial, steps 1 through 4, we don't have a way to predetermine what the type 2 error is. But we do want to keep in mind both of these errors, type 1 and type 2, when we not only are building our methods or building the test that we're going to run, but also when we interpret the results at the end, that there is a chance that we've made one of these two type of errors. And again, we talked about this in lecture, but this is also referred to as a false positive and a false negative. We talked about the pregnancy example and whatnot. So hopefully that clarifies the type 1 and type 2 error a little bit. Again, something that we want to always have in the back of our mind that because we're relying upon these methods that have randomness to them, we can never be 100% sure that we haven't made an error.